All right, definition 2.2.7, isomorphism of vector space. Let V and W be vector spaces. An isomorphism from V to W is a invertible linear transformation. All right, so it's going to be onto, and it's also going to be linear. The vector space V and W are called isomorphic if there is an isomorphism T from one to the other. We then write V equal with a tilde on it. We'll read V is isomorphic to W. All right, so in example 2.2.10, I want to show that this map here that sends a 2 by 2 matrix to a vector is an isomorphism, right? So I need to show it's linear, that it's one-to-one and onto. All right, so I'll do it in one step. I'll look at T of A plus K, A1 plus K, A2. That's T, let me write A1, B1, C1, D1, plus K, A2, B2, C2, D2. All right, we're almost there. That's A1 plus K, A2, B1 plus K, B2, C1 plus K, C2, D1 plus K, D2. And so we are going to apply the map now, and the map just rewrites the matrix, but as a vector. So we get A1 plus K, A2, B1 plus K, B2, C1 plus K, C2, and D1 plus K, D2. Right, I'm going to split it. I can first take all the ones and then all the K, A2, K, B2, K, C2, KD2, and then I can take the K out. Perfect. So this first one, that's the image of A1, and that last one, that's the image of A2. And so I proved that you can split the map exactly the way we need to prove that it's a linear transformation. All right, second, we need to prove that it's one-to-one. So I need to show that its kernel is just 0. So assume that T of A is equal to 0. That means I kind of need to complete the entry somehow. Let me write it here. Then T of A is A, B, C, D equals 0, 0, 0, 0. And so that means A, B, C, D are 0. And so A is the 0 matrix. Sorry, that's a 0 vector. Let me put it in red. This is the 0 vector. All right, and so the kernel of T is just a 0 matrix, which means that T is invertible, is one-to-one. All right, skipping the onto part. All right, so I could prove that T is onto by finding an image, but I'll show you finding its image, but I'll show you a shortcut here. We have the rank nullity theorem that cost us a good 15 minutes of our time. Rank nullity theorem. I actually filmed that one a bunch of times because my headset would stop working halfway. All right, rank nullity theorem tells you that the nullity plus of T plus the rank of T is equal to the dimension of V. So V in this case is M22. And so that means the rank here is the dimension of M22 minus the nullity. But the null space, we have it. The null space is, where is it? The null space is 0, so the nullity is 0. It's 4. All right, so if you look at what the target is, it's R4. I have something of dimension 4 inside of R4. It is all of R4. All right, so what do I have? I have a linear transformation, it's onto, and it's one-to-one. It is an isomorphism. Let me just add a conclusion. What does that mean? Let's look back at the map we've defined. All right, so it's telling you that the vector space structure of M22 and the vector space structure of R4 are equivalent. Really, we're just relabeling the elements. Instead of putting them in matrix form, we put them in vector form and vice versa. The addition and the scalar multiplication corresponds. And this is the correspondence between the elements. So if we relabel all the matrices using this, we're going to get R4. Same operations.